this so I can see questions. Or if you can let me know about questions on Zoom.
I think it's good now. Is the Zoom good, Daniel?
Good, okay.
Okay, so we have Ethan today who's going to talk about quantum field theory.
Hello, everyone, or good evening. So I've got hopefully what I would call to be an interesting talk. Less mathematical, more intuition, physics-based, but talking about quantum field theory, some of the history of it, and where these problems that we know come from. So we know that quantum field theory works incredibly well, but they take a couple things for granted. So one of it being strict microcausality. Right, we have these rules for causality that we expect to always hold true. We take ideal projective measurements, which I can show you how those lead to problems later, and UV completion. We have all these divergences that we want to get rid of, and we just hope from the start that they won't be there. So there's some hidden assumptions, if you wanted to call them, of quantum field theory. So I'm going to talk about a different way of formulating quantum field theory. It has about a 30-year history. It's the one I prefer to use. It covers all IR physics, but it's still finite in the UV. We can construct S matrix, we can do scatterings. Loop diagrams remain finite. So in the canonical Whiteman axioms, right, we can write, I hope everyone on Zoom can see. Right, so we've got my lab, your lab, built on two test functions. So we can say that the commutators outside of our light cone should go to 0, space-like separated distances. And that holds true for the low energy limit. And we can write this for all, I'll just write it as for all G minus F squared is less than 0. So this will allow for us to hopefully not get superluminal signaling outside of the light cone. Commutators won't commute. But this has a problem when you try and do loop diagrams. It doesn't go to 0, it goes to infinity. So,
sorry, I'm not a physicist.
Okay.
What do you mean G minus F squared less than 0?
So your space-like separated support test functions will be less than 0. That's when this will hold. But when you bring the space-time points closer and closer together, they're not less than 0. It is 0. So
I guess asking what's the product structure here?
I'm not sure how to define that, I guess. What do you mean product
Like,
structure?
because I thought they were like functions into like.
Yeah, test functions.
So if it's squared, it should be bigger than or equal to 0 always. So that's why I think there's a different product going around.
Yeah, you get these divergences at the high energy limit. I'll get more to causality stuff. Maybe I can answer your question later.
Sure.
Yeah. Okay. But QED will complicate how we think about causality because it has to be built on gauge invariant observables or gauge invariance. So point-like charges and fields, like they're not honest observables. They're only properly defined for gauge invariant algebras. So I'll go into a little bit of a review, and then we can get to more of the new stuff, because I'm not expecting much to be known, because I kind of am going to bounce all over the place. So we'll start with some scattering theory. Right, so scattering theory is operationally how we can apply Q of t. So you can have, an output is the operational outputs that we get. So an S matrix must exist. That comes from, right, the Hagerl structure. Sorry. Okay. It's the biggest talk I've given, I'm going to be honest. Okay. HGGRULL structure is given by time to a 1t defined for a n t. This is f1 of n times your vacuum, right? So this will allow us to get in and out states. So you have a particle coming in, how will it scatter is the question. So S-matrix theory, or the Hagerl just states that an S-matrix theory must exist. So you have to be able to do your scattering. So this is as t goes to plus or minus infinity. Yeah. So, right. So, yeah. So we can show. So when you go into UV completion, this will still hold. Yeah. So one of the important things when you do scattering theory is to be able to calculate scattering amplitude. So what can you do in a collider, in collider physics? So the L, S, Z reduction, we'll say the amplitude, the sum from J equals 1 to N, it's not written nicely, J equals 1 to N for P J squared minus M squared G tilde, right, so that's just the Fourier transform of your time-oriented endpoint function, times P1 all the way to Pn. So this will just allow us to eventually compute scattering amplitudes. So what will you expect when you do collider physics? Yep?
Do you care to explain kind of like, because I'm not a physicist, like what is this expression you're writing? So what does it calculate for you, or what is it?
So scattering amplitudes. So this is just the formula that you'll want to hold when you do collider physics. Those are the measurements you'll make. So what are the amplitudes of your scattering?
What's G tilde?
G tilde is the Fourier transform of your endpoint function, which I don't actually have written out. But
And the P's? What's the
P's you'll be looking at momentum. Or yeah, so P of J is the external momentum, so coming into your scattering.
Okay.
Sure.
Okay. Yeah.
So the left term is like a support term, right?
Yeah, so
Momentum. Okay.
that could be a way of thinking about it, yeah. Okay. So I'm moving, actually not at it pretty quickly. Okay. So
Question from Zoom.
Yeah.
What's the definition of the A's and the N's?
oh, here?
Yes.
Okay. So yeah, I guess I skipped quickly. Okay, so so A of t of your function, so that's the time translated wave packet of your smeared creators. So yeah, how can you make things act non-locally to get actual measurements? I'll get to why things have to be smeared fields and not point fields in a second.
Sorry, what is any, what, smear field?
Yeah, so I'll get to more definition in a minute, but basically, because you can't make a measurement at a point is one of the problems. You actually average over space-time.
Okay.
I'll explain the motivation behind that right now. So the history of quantum field theory is something that does interest me a lot. So we can start of when we started thinking about why things might want to be non-local, why we might not want the Whiteman axioms as they're normally quoted in the textbooks. So I refer to these as over-localized, just because they are defining space-time at a point. You can't really define anything at a point meaningfully, and so that it's not shocking in the limit that you will get infinities when your commutators come together. This has been seen when you look at current operators. You get what's called the Heisenberg singularities that come together, and they go to infinity. So you can't, basically all that means is you can't define space-time at a point. So in 1931, Paris and Alice, I know I'm mispronouncing their names, but argued that in relativistic quantum theory, you actually can't measure field strengths of the electron. So in 1933, Bohr and Rosenfeld actually replied to this and said, well, you can because you made the flaw of assuming that you can make a measurement at a point. And they wrote this out by saying to actually meaningfully define f mu nu as a function of r, where r is your space-time volume, 1 over space-time region integrated over the region of f mu nu of x in 4 space. So this is just saying that any meaningful measurement, any meaningful definition, whether you're talking about QED, QFT, can't just be defined at a point. So then Whiteman came along in 1955 and said, he actually formulated this mathematically, and I went and read his paper because it was interesting to me, where he did show that yes, you can write the commutators as he did, but that was only an approximation, and that actually anything meaningful needs to just be an average. Yeah?
Sorry, what's the little f?
Little f, it'd be your test charge. Yeah, it'd be a test charge. Yeah. So Whiteman said that what he wrote down was the correct local approximation, but that all fields are operator valued distributions, so they must be smeared against test functions. So why have I been going on about localization? Well, because Raphael Sorkin in 1933 wrote a paper on what is referred to as his impossible measurement. And he said, if we take 4 things, we don't want superluminal signaling, makes sense. We don't want our future light cone interacting with our past. Strict microcausality, as Whiteman defined it. Ideal measurements, ideal projective measurements, and the localization of measurements. And he ended up finding that that actually meant you needed superluminal signaling, and that's what it led to. So that was a problem in quantum field theory for quite some time. How do we make sense of this? If all of our laws, all of our rules that we publish in our textbooks lead to the idea that we must allow for superluminal signaling, faster than light information travel, that's a problem, that's a paradox. And so I looked into this, and I've talked with different students about this, and professors, and I wrote a paper on this that showed that actually when you do get rid of this over-localization, you have to change the causality bound, which I will explain properly soon. You end up finding that the paradox dissolves. It doesn't resolve the paradox because there is no paradox. The paradox only comes from our assuming that physics must be local, that it must be ideal. Yeah. So oftentimes when we work in non-local quantum field theory, you get told, oh, well, it's non-local, so superluminal signaling. Ideal question, makes sense. But that's not the case, because you actually have a microcausality bound, and if it's formulated correctly, you will see that in the low energy limit, scattering theory holds, causality holds, but then it just says that this is an approximation that works all the way up until your non-locality scale. Now that is something you will define. I define it to be the Planck scale in the work that I write with me and my supervisor. But you could make it lower, but we have no observational evidence of it being lower, other than minor things. But we know that causality and these constraints do hold for what we have. So one more piece of motivation, and then, because now we'll actually get into some QFT. So there's a paper written, 1949, by Feynman and Dyson. Well, Feynman wrote this one, but a lot of the work was also done by Friedman Dyson. And the paper, if you're interested, is called a Spacetime Approach to Quantum Electrodynamics, where what they say is when you look at your tree graphs, those are actually spacetime integrals. So yeah, so interactions will happen at space-like events. So we integrate over the space-like events, and the diagrams are just the bookkeeping for these integrals. So
Excuse me.
yeah.
What's a tree diagram?
Without a loop correction. So, if I just wanted to do, it's fine. That's a tree level diagram. But then if I wanted to add a one loop correction, yeah, I guess I should have led with that. Good question. Yeah, so loops are just corrections to your momentum. Yeah. So we can write out the Lagrangian QED, LQED. That's equal to minus 1/4 F mu nu, psi bar. I'll define these in a moment. Dirac matrices, covariant derivative, minus your mass, and that's, okay, so d mu, your covariant derivative, is mu plus I a mu, field strength, so potential, and then F mu nu is equal to, that's your field strength, your Dirac matrices, so this is what you would use to calculate anything in QED. So we can define an interaction density of x. So this is equal to e to the minus e. Sorry. So these are all functions now of space-time. Dirac matrix E. X. Yeah, I'll explain this all in a second. So then that's mu x. So then this will give a Hamiltonian, your interaction of function of space-time, which is positive e. Now this is up to sign conventions. E x mu x a mu x. So the goal of Feynman and Dyson's work was to find a different way to describe quantum field theory instead of the normal propagators and whatever. So for this, we can write a covariant S matrix. So S is equal to time-oriented function. Yeah, coordinate xp of minus I integral d4x times an interaction with a function of space-time. So, yeah, so this is just saying we can map our in and out states and get real world answers that we can, use for collider theory. Yeah, so this is a space-time viewpoint where the interaction is just a space-time integral. So perturbation theory expands it, right, and then interprets it over vertex points.
Question.
Yep.
Your interaction density, what kind of, I don't understand the interaction that's happening here. What's the...
Particle interactions.
Just between like the same, like...
Same particles. You can define it for as many particles as you need, but like if you're just doing like an electron-positron scattering or something, yeah.
Okay. And this E here is just...
Electron.
The electric charge?
Yeah, electric charge. Yeah. So we can use this to define our in and out states. So what's called the Dyson series, we can expand to second order. So S is equal to 1 plus minus I integral d for x. I promise this doesn't mean so this is just our first term. Plus minus I squared over 2 factorial. This is long, I apologize. For x d for y t h I of x h I of y, and then you can go to higher order terms. So this first term is no interaction. The second term, you'll add to 1 vertex. And then this term, you'll use for 2 interaction vertices. So it's just how you will, there's more for loops, but these vertices so they don't blow up to infinity. So this was how you can explain it like that without getting infinities. So if we look at the Feynman propagator, then we want to calculate loop corrections of x minus y. So this is equal to integral d 4k over 2 pi to the 4th times, and this is what makes it nice, because now you're multiplying your propagator by e to the minus I k dotted with x minus y over k squared minus m squared plus I epsilon. Normally, you wouldn't have this factor of e, but this will keep it from blowing up to infinity when you go to your loops. I won't walk back over there. So we take a different approach to doing this than just a space-time approach by integrating over space-time, but yeah.
Sorry, I think you do always have the exponential, otherwise it will be independent of
Never mind. Yeah. But when you write different propagators, yes. But in this one, you do have it.
So what is this?
So when you want to calculate what's going on with your loops, you'll use the propagator to try and explain how the momentums and stuff transfer.
So when you mean calculate what's going on, you mean like check the
Corrections to momentum and things like that. that happen at higher orders. When you do
Higher
loops.
orders.
Right, so the more loops. Okay, so when you do scattering theory, you can do it tree level, right? So just no loops. But then you want to do corrections to make it more what you'd see in experiment. You add loops, but that becomes a problem when you do. Right, loops have UV divergences. So the more loops you add, and then there's also things you have to add. So you have to have higher order counter terms, which effectively just become infinity minus infinity to get it to be a regular solution. Yeah.
Just to help Trevor, like he wrote fields in the Lagrangian, psi of x and psi bar of x.
Yeah.
That finite propagator, it's not quite the time-ordered correlator of vacuum psi of x, psi of y vacuum, because they're fermions, but if they were bosons, then it would be exactly that.
Yeah. So Dyson in 1949 showed that the space-like approach to QED is not just a convenient formulation, it's not just interesting, but that it was actually equivalent to what was formulated by Tamanga and Schwinger. So this is a fully consistent covariant way of doing quantum electrodynamics. Yeah, all right. Yeah, okay, so now once we take seriously that fields must be distributions, right, coming from Whiteman, that interactions, can come from their space-time integrals, it becomes natural, right, to treat observables as near fields. And we see that everything that we have to do in physics can't be described at an absolute point. Then maybe we should think about formulating quantum field theory on that instead of formulating it the way we do as being local. Right? If we formulate it not to be mathematically convenient, but to be physically convenient, can this get rid of the problems, right, that are seen through Sorkin's impossible measurement, or just the divergences in the mathematics that seemingly only show up due to this overlocalization? So, yeah.
What was the first thing you said? The impossible measurement?
Yeah, Sorkin's impossible measurement. So if you take, so if you have idealized projectors, you want absolute causality, you want a localized measurement, and no superluminal signaling. Not all of those can hold. So Raphael Sorkin showed this, and it's called Sorkin's impossible measurement. It's a problem, right? Because we don't want superluminal signaling, but quantum theory is built on these idealized measurements and space-like points, or space-time points. So maybe we should formulate quantum theory differently, and that's what I'm hoping to convince you of now that I will finally be getting into new physics, not stuff that happened in the 50s and 90s. Yeah, okay. So, okay, so the way I think we should do this is we should start by making the theory non-local from the start. Not non-local in the sense that we will get superluminal signaling, but in the sense that we don't have these strict bounds. So we can define what we call a regulator, a UV regulator term, where you can just say generally f of z is equal to e to the z. So it's some exponential regulator. So we can take it to be the covariant, right, Laplace, the long tree operator, box is equal to minus g mu nu d mu d nu. So let's define this. We can write it as f of box over, call it m star squared. M star squared is some non-locality scale. So we'll just keep it general, but you can take it to be the Planck scale when it turns on, if you wanted to call it that. So when does this effect start to show up? Normally this is just equal to 1 for anything less than Planck scale or your non-locality scale. So you can write it as a power series, f of box over m star squared would be equal to, we're going to sum from 0 to infinity of 1 over n factorial times box over m star squared to the nth power. So for some constant mass scale, this series is convergent. So the issue, so first we'll write it like this. Then we'll say, okay, so f of box over m star squared. We'll go through a Fourier transform to become f of p squared over m star squared. But if we recall this, that won't help us if we dress our vertices and our interaction, like our kinetic operators with this, because it'll still blow up. Yep?
Sorry, what does convergence mean? It's an operator.
It'll allow the series to, this will go to 1 in the limit. Yes, you could expand it as a series. Here. Wait, what did I written?
So convergence just means you can write it as a formal combination of
Yeah.
operators?
Yeah.
Okay.
I guess that's not the right word. I apologize, yeah. So this will blow up, so we can Wick rotate it, which then this becomes f minus p squared in Euclidean momentum space to m star squared, which then this would be equal to e to the minus p squared over m star squared. And that'll allow us to, as you go to higher and higher scales, cancel your infinities with something tied to a physical observable, that being the non-locality scale. So,
I have a question.
yep.
You just out of curiosity, why m star squared and not just m star? Just out of curiosity. Just convention.
Yeah, it's. I don't know if I have a good answer for that. So, some of the history about why this was introduced. So, 1991, my supervisor introduced this as a way of doing the same thing string theory did, basically. Because if you look at the exponential, you can write in string theory is e to the minus alpha, which alpha is the string tension, and then you've got some other term in there. So, yeah, I actually don't have a good answer for that. I think it's maybe convention. There might be an actual reason, but I know.
Physicists have this thing called units.
Oh,
And,
oh yeah.
derivative
Okay.
side units of one of our lengths, and we
Yeah,
work
never
with
mind.
speed of light equals to 1, so mass is one of our lengths. So
Never mind,
two
yeah.
masses
I
that
should have
are
said
units.
that L star is equal to 1 over m star. We wanted to define a Planck length. So that's a really good answer that I wish I had been the one to give. Okay. Go ahead.
Sorry, when I was thinking about the convergence thing, I missed the step of how'd you go from the box to p squared?
Oh, you can show through a Fourier transform that you can get it p squared, so in momentum space, and then you'll want to Wick rotate into a Euclidean momentum space.
Okay.
Yeah, I should have emphasized that more.
It's fine.
I'm sorry.
Yeah, it's just,
Yeah, okay. So now we have something that we can dress our vertices in QFT. So let's describe what we can call a regulated or a non-local observable. So we'll take this as f of x, and this is just simply f of box over m star squared. So pretty easy to see. You're just dressing your observable. Yeah, and then here I've got L is 1 over S. Okay, so we can have some regulated smearing where we will write this out. It's the integral d4x f of x, some test function. Is your non-local observable. And then this is equal to d for x, d for y, f of x, k f of x minus y, or y. And so this is some, like k of f is some smooth kernel induced by f. So, yeah.
Little f. Lowercase f.
Oh, it's a test function.
Okay.
Yeah. So, how can we observe these things? Is the question. Yeah. Okay. So now we can look at the algebras of some operationally accessible observables in some space-time region, and write that as A of f, because it's regulated. That's equal to the von. Yeah, so that's the von Neumann
Can we skip back
algebra.
for a second?
Yep.
I don't get how that first line is equal to the second line. Like, how are you going from capital F to that integral? How is anything? What's the relationship between the first equality and the second one?
Oh, okay. So I don't have the full expression of this, but this is just
No,
some
not the
smooth
the
kernel.
of that.
Yeah. So.
Like literally top of the board to the second equality. How did you get that? Or is it two different expressions?
Yeah, it's two different expressions. Sorry. Right, because this would be in terms of x and y.
No, like the
Yeah, no,
top-
this one and this one.
No,
No, the very
top.
This?
Top,
Yeah.
Oh yeah, this is just a definition of saying this is regulated. Oh yeah, these are different. Sorry.
Oh, okay.
So this is
Alright.
saying.
Sure.
Did I
read O of F, right?
Yeah,
Okay.
Oh, okay.
that's a good catch. Sorry about that. Yeah. So this is saying you've got some non-local observable, and then this is it on a test function.
Sure. Okay.
Thank you for catching that, because yeah. Okay, so that's some von Neumann algebra to define some non-local observable, which this will have a point in a second, of f, a test function with support, some space-time support, which is a subset of your space-time region. Yeah. So, support. Yeah, so this is a quasi-local way of looking at observable algebras. So, at these non-local scales, we can redefine what is, quasi-microcausality, asymptotic microcausality, whatever you'd like to call it, in terms of a bound. Yeah, I'll write it underneath here. So, can you see this, Lo?
Yeah.
Okay. Order 1 of f of test function, f space-time region 2 of g, other test function. And we can have this bound where this must be less than or equal to Cn, so some number that you can relate to a non-local scale of 1 plus m star squared. No. Then rho, your density, rho is the input space-time spectrum between your supports minus some number to power e to the minus alpha m star rho. So instead of it just being less or equal to 0, it just must be less than some function of our space-time and then the region.
Sorry, can you say again what rho is?
So rho is the so input space-time spectrum between supports. So what's going on between?
Sorry, I'm not sure I follow.
Okay, so what you want to look at is how are these smeared fields interacting? So showing that they're not still blowing up, I guess. Yeah. So through this bound, we can say that Sorkin's impossible measurement through local projectors and all this other nonsense and idealizations just vanishes.
Why?
Why? Oh, because we're no longer asking for strict microcausality, which is one of his assumptions. So since we can't have strict microcausality, we also don't have strict locality. So two of the pieces go away, which needed to be violated anyway for the paradox to resolve itself. So from the start, they're not there, so they can't form the paradox. So it kind of dissolves, if that makes sense. So like the reasons for the paradox are ideal measurements, localized spacetime, localized measurements, and strict microcausality. But if we don't have strict microcausality and we can't define spacetime at a point, two of the things are already violated, but those ideas were baked in from the start. So if we get rid of them from the start and we can define something new, there's no a paradox anymore. So it's resolving it by just getting rid of it, if that makes any sense.
So
Yeah.
really just
Sorry, just a question on the left-hand side, is that the norm graphic?
Yeah.
So which norm are you referring to?
I'm not sure. We can talk after. Sorry. That I want to skip because that's just a lot.
So
So I
Rho
think-
has some known expression in terms of F and G, because that's the only way it can be F and G independent.
Yeah, I don't have it here, but I can pull the paper out of my bag and we can talk about it after if you want. But so we're almost at 7. So I think I'll just conclude, and then if we want, we can talk more after. But basically, I hope that I've shown you at least an introduction of why this is something that should be looked at, why it's cool, why it's interesting. Maybe there's other cool things we can do about this. So when I was looking into Sorkin's impossible measurement, which is, I know I keep talking about it, but it was kind of the eye-opener for me. Because I had written papers on non-local quantum field theory before, but I didn't realize that it actually had consequences. Another consequence, for example, we talk about there's Newton-Wigner and Foldy-Woothausen localizations, which are two different descriptions that we have for how we will localize. And they cause problems. So, Newton-Wigner is what's preferred by theorists, and that's where we say localized to a space-time point. But then when you want to do beam alignment, you want to go to CERN, calculate something, actually make a measurement, they'll use Foldy-Woothausen, which is, again, an average over some non-locality scale. So if we can find some non-locality scale that works for all definitions from the start, they rectify, they come together. They're the same definition. If from the start we define localization differently, there's no two different kinds, you can still get local approximations, but it all has to be averaged over. So let me just see if there's anything else I wanted to say. Yeah, but I hope you'll agree that locality, microcausality, we should maybe look at the different assumptions of what we built quantum theory on and try some new stuff, right? So for string theory is non-local because they're extended strings. So maybe we should look at formulating quantum theory, which is only in 4 dimensions instead of 10, or see what else we can do. Maybe there's cool problems that can be tackled. Yes?
You keep on mentioning that you can sort of start looking beyond locality by using the smear.
Yep.
But I don't necessarily see why smearing would allow you to talk beyond local. I'm just thinking topologically.
Yeah, okay, so if we wanted to think about localization sort of the normal way in physics where we're just defining a space-time point, however you want to define that point, whether it's infinitely
Yeah, so
small or
local
whatever,
smear is just-
but if we make it non-local from the beginning by smearing it, so we can just say you can't have a very fine, well-defined point. What
Yeah,
you
I
have is some
understand that, but-
smeared field where it's something around it. Yeah.
Yeah, so local to use, or to, I guess, to this, in this setting, is just points.
Yeah, but
Okay,
points
yeah.
at a certain length scale, right? So normally we don't define a length scale for our localization, but to say, can we define one, whether that's the Planck length or 2 times the Planck length or something like that, these scales can make things non-local, and it's an
But you can
actual.
still smear within the boundaries of locality, right?
You can, and if you do it, these problems solve themselves as well. So what I'm hopefully arguing for, and maybe a little convincingly, not sure though, is maybe we should build it in from the start instead of assuming these things about locality that do cause things like a paradox, Sorkin's paradox. Now you can make it go away by making fields act non-locally and do non-local measurements and whatever, similar to what Bohr and Rosenfeld said when you make your measurement of the field strength. But if we can have it baked in from the beginning, our ideas for causality and locality having to not be super well defined, then it solves the problems at the door. If that makes sense. But anyways, thank you guys for listening. I'm sorry I was a bit all over the place. It's the biggest talk I've ever given. You guys were a great audience. Thank you. Is there any more questions?
So if you take this idea seriously of inserting e to the minus momentum squared over Planck mass squared
Yeah.
to make things finite, then you could compute something where we know the answer, like the
Yeah.
beta function of Yang-Mills theory.
Yeah.
Or it's a loop calculation. You would get a divergence if the Planck mass were infinite.
Yeah.
So the answer you get must have some term that's proportional to Planck mass squared,
Yeah.
the part that's infinite, and you're subtracting that away, right?
Yeah. So when you have your functions that are blowing up to infinity, because this is minus p squared over m star squared, which is your Planck scale, that's decaying exponentially, right? Because it's minus, so you get cancellation that way in a physical way, if that makes sense. But you can compute things and get the right answer. So right now I'm working with a colleague of mine on next to leading order corrections to gluon fusion to Higgs, which is famously nasty when you do virtual loops. But the equations become finite and they're in a closed form. So they're actually something that we can compute. And this might become important in the next few years, decades, when we build the 100 TeV collider to measure the self-coupling of the Higgs. Maybe we will want these very high-order corrections if we want to make these precise measurements, right? So the more loops you add, the more difficult these things become, so you need more counter terms. But if we can get rid of the need for those counter terms from the beginning, maybe we can get some sensible answers that could be useful. Because it makes the equations easier to calculate because they're all in closed form. When you do scatterings, so when you're calculating a scattering amplitude or something like that, that's where these divergences might show up.
I would think making the space-time dimension 4 minus epsilon is like much more mild than putting an exponential. I would expect an exponential to make your expressions not have a closed form.
Yeah, so we can talk about it more after in more detail. But yeah, so it does actually give you a closed form because it gets rid of the need for these extra counter terms because you're just suppressing it from being built in. But in the IR, your e to the minus p squared over m star squared just goes to 1. So by our definition, it will just be 1. So you're not changing IR physics, you're only changing it where these divergences show up.
Well, I would say these terms proportional to the Planck mass are
Yeah.
counter terms.
You could call them that, yeah.
It's like moving the problem somewhere else.
I guess, yeah, you're moving it earlier, the solution earlier, I think is a good way. Instead of getting these nasty, master integrals or whatever and adding in counter terms at the end to try and solve the problem, we start with the solution from the beginning. But I do agree, I see where you're coming from. Yeah, so I think we agree in the same, and maybe in different ways. Is there any other questions? Okay, well, thank you guys. Or is there any on Zoom?
Let's see. I had a question though.
Yeah.
With the second last line of the AF of O.
Yeah.
Yeah. What's the notation with the equal sign? You said something about von Neumann algebra.
Yeah. So you're just defining a non-local algebra. So how can you go ahead and compute things? I'll pull out my actual paper that has all this stuff and not just the quick jotted notes afterwards.
Sure.
But yeah.
On the same line, I guess, not about like what this means formally, but just like intuitively, what is AFO supposed to like represent? Just intuitively.
I guess I should write it's F. Make that a bit. So it's just how you would define a normal algebra. You would just change it to be non-local. It's kind of just to attest that every step in the mathematics is non-local. But that's okay when you take it in a local limit. Yeah. Any other ones?
Sorry, can you, I did not understand what you just said.
Here, we'll talk about it after, sorry. But yeah, I think that's, okay, thank you guys.